Oh, good afternoon. It's Friday here. Yesterday was a good day on the market. A number of indices hit records. Let me put my mic on and repeat what I said. Yes, yesterday a number of indices hit new record highs. Today, the market is doing about nothing. It was down a little the last time I looked. So typically, Friday is a good day, as anybody who's doing that day of the week would probably know. Okay, we stopped off on this butterfly spread. Let's look at that. We didn't get through it. So let's recall our butterfly spread. Okay, in a butterfly spread, we do the following. And remember, this is in figure 12.4, page 325. Good. Here we buy two calls. So we hold two calls. And one at strike price, K1, and one at strike price K3. Now, I said that most books use K for the strike price. I've seen some books use capital X for the strike price, but K is more common. Now, we sell or write two calls. So we're buying two calls and we're selling two calls. But the two calls that we sell are both with strike price K2, where we have these strike prices are related by the following. That K1 is strictly less than K2, which is strictly less than K3. Because of this, we get the effect of a butterfly, it looks like. Okay, so let's look at these. Let's see if we have a blue pen here. Let me get a blue pen, guys. Here we go. Okay, good, great. We'll get a red one too. Okay, so let's look at these graphically. We're going to look at the following. So we have the buying two calls first, one with K1, one with K3. Now, you know, we'll say since K1 is less than K2, which is less than K3, what do we know? Okay. These are calls. So the calls give us a right to buy. So if we get a right to buy the stock at a lower strike price, our premium must be higher. So this, we'll say this is O. Let's call it call 1. Must be greater than O of call, say, K2. This could have been K1. Is greater than O of the call K3. Okay? So remember, we had said this before, that for a call option, the lower the strike price, the higher the premium. Because remember, you can buy at that strike price. Then you can sell at the spot price. Okay, so let's see what this guy looks like. Let's put these together. First, we'll put a call at K1. And this is the hold call at K1. Okay, so we said that K1 was less than K2 and K2 was less than K3. So let's call this guy K2. And so what happens? Then the value of that, let me make this K1, excuse me. The value of that goes here. If we're less than K1, if the stock price is less than K1, then it doesn't pay us to buy it at K1. But if the stock price is higher than K1, then buy at K1, sell at S. So now our value goes up here. This is the value. And we have the premium. Now the premium is high for this. Let's see if this looks high. Let's call this O C1 instead of K1. And we'll go up like this. This is our pi. Now, let's look at the holding of the call option with the strike price K3, where K3 is the biggest of the strike prices. So now K3 has to be somewhere out here. K3. Okay. Now what do we get? Now since K3 has the highest strike price, it will have the lowest premium. But again, if we're below the strike price, the call option is worth nothing to us. If the stock is above the strike price, then we're in the money here. So we can make a profit. So here we go up at 45 degrees. V. Let's write this down. Hold C at K3. Okay. And we also have the profit from this. Now, the premium is less, is much smaller on the call at K3 because K3 is higher. So we get something like this. This is O C3. Okay, now what do? The last thing we do is we sell or write two calls at K2. Let's look at that. Let's see. Let's try to do this here. S dollars. Okay. Now, we have, since we write two calls, what happens? We make money, we get the premium if the stock price or asset price is lower than K2. So let's look at that. So K2 is here's K1, here's K3, so say K2 is over here. So K2 is between K1 and K3. And what happens is we get something like the following. Now we have we have this goes out here, and then it goes down here. Now this goes down 2 for every 1 horizontal, because we have 2. We're writing 2 calls at K2. So notice this is not 45 degrees. This goes down 2 vertically for every 1 horizontally. And so this is right 2 calls at K2. Now, when we write 2 calls at K2, if the stock price is less than K2, what happens? We're going to make a profit here. So we're going to do something like this. This is going to be 2 O C 2 CK2. Let's just do a K2 here. So that's that premium. We get that premium. And again, what do? We go down, since there are 2 calls, we go down 2 for 1. This is pi, and this is V. And both of these go down 2 for 1 horizontal. Okay. Okay, now let's put them all together. In the book, they don't separate them. They just put them all together in one figure, which it could be a little confusing. Let's put these all together. Okay, in other words, we'll add the ordinates. Okay, and what do we have here? Let's look at dollars. And then let's look at the stock price. Okay, so what do we have? We start off with, we have to pay the premium, and let's look at profit here. We have to pay the premium for our, to hold a call at K1. So this is O call K1. And remember, K1 is smaller than K2 and K3, so it has a decent sized premium. So we'll say that this is K1. Now, what happens here? We start going up here because of the following. Because we have the profit from selling 2 calls at K2. Now, selling 2 calls at K2, K2 will be less than, the premium will be less than K1, but we have 2 of these guys. So we have something that looks like this. This is 2OCK2. And we're going to make that if, let's call this K2. So we just pick up the premium if the stock price is less than K2, because the option will not be taken at that point. And then finally, what do we have? We have the, we hold a call at K3 here. So now what's going to happen is here we're going to start to go down 2 for 1. And we're going to hold a call at K3. So the K3 will have the smallest call premium of the 3. This is OCK3. Remember, we buy that call. We buy the call at K1 and the one at K3, and we sell 2 calls at K2. So let's look what happens here. We get something that looks like the following. This is the combination. And actually, this in fact is the payoff or the value of that combination. Well, actually, it's the profit of that combination here. So the red looks like a butterfly, if you use your imagination. Okay. I think that my explanation here is a lot easier than the one in the text. Although there is an exercise about how the premiums should relate to one another that we will give. I'll probably give homework on Monday. Okay. Now, let's get into another area. We're also dealing with options. And this will be option pricing. And we have 2 ways to look at this. There are 2 models, and these are 2 main models. One is discrete, and when we mean by discrete, we mean discrete time. And this is called the binomial lattice. Then we have another one whose mathematics is a little more difficult, and considerably more difficult, called the continuous time. And this is the Black-Scholes model. Okay, so first let's talk about the easier one. And in fact, with computers now, the easy one is easily implemented on high-speed computers. The continuous one, you can calculate that by hand. Okay. So let's look at the binomial lattice. Option pricing. before these models, people didn't really have an idea of how to price options. Of course, the market was pricing them, but nobody had a theoretical idea. And this is due to Stone in 1969, and was rediscovered, or a similar model was in Cox and Ross. (1976). Remember, I think that Ross was the developer of arbitrage pricing theory. Now, the binomial lattice model does the following. This assumes that in any period, of time, of course, the price of an asset and most often this is used for stock, can go up by a multiple equal to u, which is strictly greater than 1. Or down by a multiple equal to d, which is strictly less than 1. Okay. Now, how are u and d related to one another? Now, u is greater than 1 plus r, and this r is our period interest rate. And remember, we had that 1 plus r equal cap r way back. We talk about the rate of return. And that this is greater than d. The reason for this has to be true. This relationship has to be true for no arbitrage. Why? Let's see why this has to be true for no arbitrage. If this wasn't true, else, if u was less than r, okay, the return, then we could short the stock let's call it an asset. Okay, because we know that the up move is going to be less than 1 minus r. 1 plus r. And use our proceeds dollars to invest in a risk-free asset. And this is yielding an immediate risk-free profit so which is an arbitrage. Opportunity. Okay. A lot of the proofs in financial engineering use the argument that you can't have an arbitrage opportunity. Of course, there do exist what we might call arbitrage by mispriced stocks, but in theory, we have to assume that most models assume that there's no arbitrage. Okay, now let's look at this binomial lattice. It said we could go up by U, and we could go down by D. So let me look at figure that's in the book. Let's look at figure 11.1, page 297. Okay. So let's start off with a stock or asset that has a price S. Then if we'll say the price can go up in one period to SU. Or what can happen, that price could go down in one period to SD. Okay. Then in the second period, let's call this level 1. Let's call this period 0. This will be 0. This will be 1. Now, again, if we go up again, we go up to SU squared. Or what happens? We could go down to what? We could go down to SUD. Because our first move was up, and now our second move is down. And so this is the end of period 2. Likewise, on the downside, here, what can we do? We can continue going down to SD squared, okay, or we can go down 1 and up 1, okay. And so we're going to go here to SUD. I could have made that a little better. Okay. Now, let's look at the next period. Again, we can go up again from that SU squared to SU cubed. So let's call this 3 here. SU cubed. Or we could go down to SU squared D. So we have 2 up moves and 1 down move. We can also reach that from an up move from SUD. So we can reach that here. Now, what else happens? Now, from SD squared, we can go to SUD squared. When SUD squared is going down from here, this is SUD squared. Now, we can get at this guy from going up here, from SD squared to make an up move. Finally, we can go down to SD cubed. Okay. So let's look at this. Let's write this. Ways to reach a node at level 3. And it really is at the end of level 3. There's only one way to reach this node. You have to go up and up and up. So there's one way to reach this node. Now let's look at the SU squared D. Now, we could get there by a number of ways. We could go up first, then down, and then up. Okay, what else can we do? We can go up and down. That's the second way. The third way is that we can go down first, then up and up. So there are 3 ways to reach that node. Likewise, there are 3 ways to reach SUD squared. Okay, how can we do that? We can go down, down, and then an up. Or we can go down, up, and then a down. Or we can go up, down, down. Okay, finally, there's only one way to reach SD cubed. Okay? The only way we can reach SD cubed is by going down 3 times in a row. Okay, and here you see these are symmetric. The number of ways are symmetric here. Now let's look at some important things about this so-called binomial lattice. Well, first, why is it called binomial? Okay. So let's look at why is it called binomial. It's called binomial because the probability of reaching any node take for example node S uj. So you go up j times and you go down n minus j times. At the end of period n is given by the binomial distribution. Which you probably have all seen. And that that binomial distribution is as follows. We'll say that the probability of reaching node S uj d n minus j at the end of period n, what does that equal? Equals the number of combinations that you can take, ways you can take j things out of n things, okay. The probability that you go up j times the probability that you go down n minus j times. Okay. Where Pu equal the probability of an up move and Pd equals the probability of a down move. Okay, that's our binomial probability distribution here. Let's look at this. Now, the other thing we want to know is, well, let's look at this more closely and see what's going on. And we're going to recall that n over j equals the number of ways or combinations of picking j things, of selecting j things out of n things. Where n over j, this combination equals n factorial over j factorial times n minus j factorial. Okay. Where n equals n factorial. This is definitely a repeat for almost everybody, but it's useful to do it anyway. Equals n times n minus 1 all the way down to 1. So we have n times n minus 1 times n minus 2 all the way down to 1. So 3 factorial equals what? Equals 3 times 2 times 1 equals 6. And 2 factorial equals 2 times 1 equals 2. 1 factorial equals 1. And we also define 0 factorial to equal 1 by definition. Although we won't usually see 0 factorial. Okay. Well, that's some of our elementary probability that you probably all have had. So for our example, our three-level example that we looked at, we have how many ways can you take 3 things out of 3 things? Okay, this equals 3 factorial over what? Over 3 factorial times 0 factorial equals 3 times 2 times 1 over 3 times 2 times 1, 1 times 1 again here equals 1. Okay, because 0 factorial is 1. So that's what we got. This is how we got what? We got S u cubed. Also, S d cubed. There was one way to do that. Now, 3 over 2, okay, how do you take 2 things out of 3 things? Now, there are, this is 3 factorial over 2 factorial times 1 factorial equals 3, 2, 1. Bear with me if this is all review. Times 2 times 1 times 1 again. So this is 6 over 2 equals 3. And this is both SU squared D and S U D squared. Okay, so those are the nodes there, because remember we got 1, 3, 3, 1 here. Okay. Now, so this agrees with our past. Okay. So let's do the following. What do we have here? Continuing on with this simple idea, let's do the following. If the probability of an up move equals the probability of a down move equals 1/2. So the probability is 1/2 that we could go up, 1/2 that we could go down. Then each distinct path to a node at level 4, each distinct path to a node at the end of level 3 has probability one half times one half times one half, because at the end of each level you're either up or down. So no matter where you end, whatever node you end up with at level 3, you have a 1/8 probability of getting there. Hence, what do we have? The probability of reaching as an example, of reaching SU cubed equals 1 times 1/8. There's only one way to reach there. 1/8 equals 1/8. And the probability of reaching SU squared D, so 2 up moves and 1 down move, equals what? Equals, there are 3 possible ways to reach that node, times 1/8 equals 3/8. Likewise, we're symmetric here. The probability of reaching what? SUD squared, so 1 up move, 2 down moves, equals, there are 3 ways to reach that, and the probability, of course, is 1/8. So this is 3/8. Finally, the probability of reaching SD cubed equals what? Equals 1. There's only one way to reach that. You have to go down, 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 times 1/8 equals 1/8. Okay. And these are the probabilities are the probabilities given by the binomial distribution. Okay, now, the smaller the period, the better the approximation to the continuous here, because this is a discrete model. But that's not too bad, because we have a lot of computer power, so we can compute. Now, why is it called a lattice? Okay, this is a good question. We should say, and not a tree. A lot of times we have things that we call trees. Now, in computer science and operations research, we have, if you look at this tree is growing horizontally. A lot of times we grow trees down. So the root is on the top and then it expands going down. Here, the root is on the left and expands going to the right. So these things that we call trees and lattices in computer science and operations research are not natural trees. They're growing the wrong way. So notice at the end of period n-1, there are n nodes in our lattice. Like if we look at the lattice, let's go back to our lattice here. Well, we're going way back. Hey, we're really going back here. There's our picture of the lattice. Okay, good. It's got to be here. Oh, here we go. Here we go. So let's look at the lattice here. So this is period 0. This is period 1. The end of period 1. This is the end of period 2. This is the end of period 3. Okay. So at the end of period n-1, where n is 2, at the end of period 1, we have 2 nodes. At the end of period 2, which n-1 is 3, we have 3 nodes here. Then at the end of period n-1, 3, where n is 4, we have what? We have 1, 2, 3, 4 nodes. So at the end of period n-1, there are n nodes in our lattice. So what we have is a linear growth in the number of nodes in our lattice. This is opposed to the exponential growth in a binomial tree. And sometimes we see these binomial trees in, and for example, 0-1 integer programming. Or optimization. Okay, so let's look at that. Let's look at a binomial tree that we typically get. Here we are on 13. Let's look at that tree and see where we are. Okay, let's look at a binomial tree. A binomial tree, we have the following. Suppose we start here, and we call this level 1. Then we go out to 2 nodes at level 2, and then from each of these, we go to 2 more nodes at level 3. And then, in fact, we go to 2 more nodes from each of these at level 4. And now let's look at the number of nodes. At level 1, what do you have? Level 1, you have 2 to the 0 equals 1. At level 2, what do you have? You have 2 to the 1 equals 2. You have 2 nodes. Now, end of level 3, we have 4 nodes. So that's 2 squared equals 4 nodes. At level 4, we have 1, 2, 3, 4, 5, 6, 7, 8. This is 2 cubed equals 8. Okay. So there are 2 to the n minus 1 nodes at level n of our binomial tree. So here, this 2 to the n minus 1, this is an exponential growth in the number of nodes in our tree. And you might ask, why is this? The answer is quite obvious. The answer is that in a tree, any of these we might call, say the tree only has 4 levels, then we could call these guys leaf nodes at the end, although this tree is growing the wrong way, it's growing down instead of up. We could say at the leaf nodes, to reach a leaf node, there's one and only one way to reach each leaf node. But remember, in our lattice, we had a number of ways to reach the nodes here. Not necessarily this node, but this node, there were what? To reach this node, we had 2 ways. To reach this node, we had 3 ways. To reach this node, we have 3 ways. So there is typically not just one way to reach each node. So this gives this is a computational advantage to a lattice. It's a very important computational advantage. It makes it easy to compute this because on a lot of nodes there are a number of ways to get there. Whereas in a tree, our computations go up exponentially. In a lattice, it goes up linearly. I think this is a good place to stop. In fact, I think we're almost right out of time. I hope everybody has a great weekend, and I hope everybody did well on the test. And so as soon as we get them in, we'll grade them and get the scores back to you. Thank you so much.